What is the simplest way to explain cavitation to a non-engineer?
Well, for me, I've always loved drawing the simple analogy of two people pulling on a scarf. So imagine you and I are pulling on this. You've got one end of the scarf and I've got the other end, and we're applying tension, we're pulling on the scarf. But somewhere in that scarf, there's a pinhole, there's a hole, there's a defect. There's a defect in the weave, in the stitching or whatever. And the more tension we apply, I suppose you can guess if there's going to be a tear somewhere, you can guess where the tear is going to be. It's going to be at that point of imperfection in the scarf. That's where you're going to tear a hole. And it's very much the same with cavitation. As pulp is flowing through a venturi and you're applying more tension onto the pulp. And you're going to start to cavitate now. You're going to start to form these bubbles. And those bubbles are going to form at the point of impurity in that pulp. And the point of impurity, which is analogous to that pinhole, is actually the hydrophobic particles that are suspended in the water going through the venturi. That is the weak point, and that's where the cavities will start to form. And that's also where you'll get this very intense bubble implosion. So the cavities that form there are unstable. And the minute you release the tension on that scarf, so you've been pulling it and tearing a cavity, and you can imagine if you just release the tension, that cavity is going to want to close up again. And that's what happens when you reach high pressure regions in the venturi, where the bubbles implode and release a lot of energy, extreme energy release, and that system then goes back to almost its natural state, but not quite, because in the case of the cavitation in the MACH, you've now formed all of these pico-bubbles, micro-bubbles that will stay that way. They will never go back to normal state.